It's my pleasure today to introduce a special EOL seminar. M-Cube nicely gave us their time slot and room to host this visit. We have Ebba Dellwik and Jakob Mann, both from the Danish Technical University. I don't know how much you want me to say about you guys. Of course, Jakob's is a frequent visitor to NCAR and EOL and M-Cube, so I'm sure many of you already know him. Been with DTU, I saw the first publication was 91. Is that still, it's been a while, and about 15 years for Ebba, senior scientist. So I probably will let them say anything more that they want to. I think Ebba's going to start. Thanks.
All right. Yeah, first I'd like to say thank you very much to NCAR and especially Tom and Steve who made it possible for me to come here. It's been a great couple of weeks. We've worked hard and it's been really nice to visit NCAR. So the title of this talk is Can Coherent Continuous Wave Doppler lidars be utilized for in-situ instrument calibration? And it's maybe a bit of a bold title because wind lidars are kind of a relatively new technology to be used for precision experiments, whereas sonics, which I'm going to talk about today, have been around for many decades and they're well understood. But still, so it's a bit of a provoking title that we want to improve the well-known technology with new technology. So this work has mainly been done by myself and Jakob, but we have also had good support from wind scanner team, Nicholas, Mikael, and Torben, who all work with the hardware and the technology. So this is the outline, just usual outline, objective, experiment, end results, and I'll end with a conclusion. So one limitation to sonic anemometer accuracy is that the sonic anemometer may be dependent on how the instrument itself distorts the flow. That's the flow distortion effect. And there's a lot of literature on flow distortion, but still there's no kind of consensus on how to correct for it. Some sonics come pre-corrected, like the METEX sonic and the GIL sonics, whereas the CSAT sonic, which is very common here in the US, maybe less in Europe, it does not have any flow correction included. So we thought this was a good candidate for us to test. So we bought a new CSAT and mounted it in a tower at Risu. And we started looking at the data. And that's actually what I do quite a lot. I like to look at data, and I spend a lot of time looking at time series and also at spectra. And yeah, so here is an example spectra from the CSAT. And we know that in the inertial subrange, we should have this inclination of the slope, minus 5/3. And we could very nicely see that. But also in this range, the W spectra should lie above the U spectra, and so the V should, and there should be a ratio of 4/3. And we could see very quickly that this was not realized in the CSAT sonic. So then I analyzed a lot of spectra and looked at how this ratio, when I found a good minus 5/3 slopes in the spectra, I looked at what was the ratio between the different components. And I corrected for the path averaging according to your work. And could see that we rarely reach 4/3, neither for V or for some angles for V. Yeah, so here's the wind direction on the x-axis. So here the flow comes right to the sonic anemometer. Yeah, So you see the green dots are all above the black dots, which is the W to U ratio, and kind of varies between 1 and maybe 1.2, and then it goes completely wrong when the flow comes from the back of the sonic. But this interval is quite wide. This is a 30-40 degree interval. So this, to us, was a clear indication of that the sonic has flow distortion problems.
Where
Yeah.
at what height of the ground did you start those data from?
I think it's 6 meters. We had it at several heights, but most of the data are probably 6 meters.
There's a natural, I guess my question is, there's a natural anisotropy because you're measuring that close to the ground in the variances? Well, at least in the total variance. I was just curious whether that spills over enough to the smaller scales. Anyway, I was just curious.
Yeah. I don't know the answer to that. But I tried it at different heights, and I have more heights. So I could check that.
No, it's just curious.
Yeah, good. So then we started planning our experiment. And we wanted to test whether the wind lidars can measure the same wind field as a CSAT, and also to test the flow distortion. And we planned for 2 cases. One where we measured right inside the sonic anemometer, and one when we pulled the boom back and we measure at a distance of 0.8 meters from the sonic. So this is the setup of the experiment. These are our 3 wind lidars. This is number 1, 2, 3. And they are in an approximately 120 degree difference. And here is our sonic. And you can, one obvious disadvantage of lidars is that you cannot really see where you measure. So we had to spend a lot of energy and time to make sure that we really measured where we wanted to measure. And here you can see one of our technicians holding a rotating target right in the sonic volume. That's how we tested that our focus distance was right. Because the lidars can only measure something that moves. And then we have an infrared laser, and we took a photo with an infrared camera, and we could see that we got the beam right where we wanted it, in the middle of the sonic anemometer. And we did that for all 3 wind lidars. And then, since the 3 wind lidars, they kind of form one instrument, we need to know the geometry of this instrument to a very high precision. So there was a company coming, and they used this Faro Laser Tracker equipment. And they could measure, you can see here he measures on the lens, so we know exactly where our beams are located. And they also measured on the sonic itself. So they actually also measured the exact geometry of the CSAT, but because it was quite a windy day, and they were maybe moving a little, the transducers, so we didn't use those measurements. We used the standard kind of CSAT settings. So here you could see a sketch of our setup. Our zenith angle is pretty steep compared to the CSAT. So we measure kind of through the sonic volume at 50 degrees. And these were our distances. We measured at 6 meters height, but they were about 8 meters apart. And this was the first time that these wind lidars were kind of tested at a measurement volume that's comparable to a sonic anemometer. So for the wind lidars, we measure the half maximum half width length, and it's 8 centimeters. I always say it. So we have, that distance is 8 centimeters, and the sonic has 11.5 centimeters. And then we started measuring. And here I'll just show now a number of slides where we go to increasing temporal resolution. So each color has actually two curves, and the kind of broader line is the sonic, and the thinner line is the lidar. It's also slightly darker. So here one cannot really see any difference at 2 Hertz. And then we zoom in, and we take the 10 Hertz data, and it still looks good. I mean, you could start, when you look carefully, you could see that the red is actually 2 lines. And then again, we zoom into 30 Hertz, and now it's a bit clearer. Here we have a distance between the 2 curves. And then we zoom into 60 Hertz, and then we could see it even more. So this was when we measured inside the volume, and then we moved the boom back because we didn't want to change anything in the lidar setup since we knew where we measured. And it's still quite good comparison at 2 Hertz, but when we then zoom in, you much faster see the differences between the 2 curves. Right, so this is 10 Hertz, and then we zoom in again to 30 Hertz, and now it's very visible. But it's also, of course, we have kind of optimized the timing of the 2 systems, and because wind direction changes a little bit, we could never expect a perfect overlap. Yeah, so this is 30 and then 60 Hertz. You can see quite big differences. So we now come to kind of what causes the flow distortion, and we had discussed 2 possible causes. One is the transducer shadowing, that kind of causes wakes behind each transducer. And the other is rather that the instrument structure blocks the flow, and then the flow would kind of, it decelerates on the structure and accelerates through the volume. So if we have transducer shadowing, we would imagine that the sonic always measures less mean wind speed than the lidar. Whereas if we have the blocking of the flow being predominant, we would have the sonic measures more wind speed than the lidar. And then similarly for the vertical wind, it's actually there the effects would be similar. Transducer shadowing would probably cause a decrease in the vertical wind, and Jakob spent a lot of time here actually using potential flow theory to calculate that the same effect would happen if we had a blocking of the flow. If we have transducer shadowing, we would expect a stronger directional dependence of the distortion as compared to if it was the blocking, where we would see a weaker dependence. This is just what we kind of pictured in our mind. And if we have transducer shadowing, then of course the effects are strong, very close to the transducers, whereas we measure in the middle of the sonic volume. But if we have the blocking of the flow, it would have the maximum effect in the middle. So in terms of how we would interpret our data, we thought that if the lidar and sonic measure differently when we measure inside the sonic, that would be likely caused by transducer shadowing. And if they measured the same, we would have thought then it's rather the blocking, because we measure in the middle and that effect of speed up would dominate. And if we see that the lidar corrections is the same for the inside case and the outside case, we would expect transducer shadowing, whereas we would thought it would be different if it was the blocking. So here we have a comparison of the 3 orthogonal velocity components, and we used not ordinary least square fits, but the Deming least square fits, because we don't know exactly which one is more correct. So we put the uncertainties equally, or we weigh the uncertainty equals on the x and y. And this is just our first analysis of data, and when we saw these runs, we see that the sonic, when we measure inside, and here's the sonic and the vertical is the lidar. When we measure inside the sonic volume, we measure the same, more or less, as the sonic. And the corrections are different for the vertical when we pull them out. So it was several factors on this analysis that caused us to think that it was the blockage of the flow by the instrument that was the main flow distortion effect. But this is based on quite a limited data set, and now we come for the reason of this visit was to kind of detangle this data set and look at the effect of the mean wind direction. And then we needed much more data. And now I'll come to one of the bad things with the lidars. So the beautiful plots you saw before don't look so nice anymore, and it's because this type of lidar has a big problem to measure close to zero. So whenever the green curve comes close to zero, it could measure anything. And when I started looking, I found many other types of problems. We have a lot of spikes in the lidar data. We have no response in the lidar data. Maybe it's been raining. The lenses could have been slightly covered by water. We don't know. So, So for the first analysis, we selected only data where the mean velocity on the lidar path was greater than 0.3 meters per second. And that left us with kind of a limited data set. You could see those thin black lines here. That's what we analyzed. To get more data, we tried a different approach. And then this immediately kind of looks maybe even stricter, but because I increased the interval from 0.3 to 1 meters per second, but I said I could take the data on any path. So if not, the three paths didn't simultaneously need to be greater than a certain value. It was enough, if one was, then I would analyze those data. And then to do the analysis, I rotated the sonic data to the lidar path coordinate system, and then I selected by hand good periods where everything looked fine. And then I compare the sonic lidar on each of the lidar paths with Deming least square fits, and then we rotated back to the XYZ. So this actually was successful around midnight yesterday. So we tried several things and it just wouldn't work, but this worked. So now you see, as a function of wind direction, the Deming coefficient, so the inclination of this relationship. And wind direction here. So we see a strong directional dependence. And we see a tendency. So the red dotted lines, that's where we could have transducer shadowing effects. That's where the sonic transducer is located. So there is a tendency that we see more effect near a transducer. So this completely changed our conception of the problem. And this is the outside case for the W. This is for the X and Y. And also now it's very clear that the lidar measures more wind than the sonic. So the sonic kind of decelerates the flow, and that also points to transducer shadowing effects. And then I added on the Deming coefficient fits for when we measured inside the sonics, and that's these rings here. So the dots are for the outside, the rings are for the inside, and they correspond pretty well. So that also points to transducer shadowing. And the same for the X and Y. The trends are similar here, but maybe not quite the magnitude. So if we look back, then to this kind of list we made, it seems like it's transducer shadowing that causes the flow distortion to the instrument, or it's the main cause. Yeah, so now we've done this. I now need to look at more data, and maybe we will even reprocess the whole data set, because we have 60 Hertz data in the LiDAR, but if we need to average for reasons that Jakob will talk about in a minute, and then it's actually better to average on the Doppler spectra than on the velocities. So that could help us avoid some noise. And then we want to estimate uncertainties, and we want to estimate the effect of line averaging that is different for the LiDAR than the sonic. And then we want to compare these results with the flow distortion model for the CSAT that's made by Tom and colleagues. Yeah, but preliminary conclusion is that the experiment worked. It was a success, and the CSAT is affected by flow distortion, and it seems like it's transducer shadowing effects. So to answer the question, I think in principle we could use this technique to calibrate in-situ instruments, but we are not, we're not really operational. This is a lot of small things to figure out still. So thank you very much for listening.
Call the company behind the CSAT and ask them what kind of
If you're scratching it.
They don't know, right? They are very interested and positive.
Yeah, they compare my model to the firmware to correct.
Have you considered looking at a fancier moment? Let's say you plotted DUDT from the sonic and DUDT from the LiDAR. Would that give you more of a signal to show the difference? If you put the emphasis on a harder thing to measure, is it going to show up?
This was hard enough.
No, but you just, okay,
Yeah.
normally U just looks Gaussian, but DUDT does not look Gaussian.
Yeah.
Just a thought.
I could say that even though the full width half maximum of the LiDAR is 8 centimeters and of the sonic is 11 centimeters, then the averaging effect is very different. Actually, the LiDAR is averaging much more than the sonic anemometer, and I'll come back to that.
Oh, okay. Yeah. I was just curious.
But this is of course the first and the simplest analysis. We can see how good it turns out, and we decide how strong it is.
We can take more questions after my talk, so also for Ebba. All right, I'd like to thank Don, who is babysitting in Colorado Springs today, and Scott for inviting me here. And I'm continuing Ebba's presentation now with the focus on the one problem she was mentioning, namely that it's difficult to measure close to zero velocity. So these are measurements from a conical scanning LiDAR, and usually you fit a rectified cosine to that to get the wind direction and wind speed, where you cannot get the sign of the wind speed, but you get that from somewhere else. But you see at close to zero velocity, the LiDAR cannot really measure very well. And if you had a lower wind speed case, this is over a forest at 175 meters. If you go down to a lower height, 57 meters over this forest, the winds are very low, and you see a lot of problems getting close to zero. Like you cannot get it within a meter with this instrument. And this instrument is a so-called homodyne continuous wave coherent LiDAR, and I'll come back to what that is. Another thing is that we want to do a lot of measurements where we use 3 simultaneous lidars and scan around to map flow around the turbine or any structure. And it's almost impossible to plan the experiment, so you will have never have the flow perpendicular to one of the beams. No matter what you do, one of the beams will have the flow perpendicular, so you'll have 0 velocity on one of the instruments. So not being able to measure close to 0 is a problem for us. And I just have an example of what we have been doing, and this is mainly due to Eric Simley, who is from University of Colorado. He got a Fulbright grant to go to Denmark for a year, and his purpose was to make this experiment where we had 3 wind scanners here, here, and here in front of a V27 turbine, and he would like to study the inflow in front of the rotor. He was doing that by positioning the 3 lidars at the blue dots and then scanning along these lines, even right through the rotor and a couple of rotor diameters upstream of the rotor. The kind of results he got was like this. Here's the lines he was scanning along, and this is the U component, the component in the mean wind direction. And what you see here is that the flow stagnates in front of the rotor, even behind the rotor. And you can also see on the V component, the transverse component, that the flow approaches here, and then it gets a negative component here. That means it's moving towards the negative part of the y-axis, and you only see half the rotor. You can see the other part of the rotor here, the flow is going in the other direction. Finally, in the W component, the turbine is rotating positively with respect to the mean wind vector, so the blades are going down into the plane here, but that means that it washes the air up, so you get a positive vertical velocity in this area. All these are 10-minute means, but Eric would like to use the data set also to study how the turbulence will change as it approaches the rotor plane. Anyway, he will have some problems with getting close to 0 velocity. So the first data I showed was from this conically scanning lidar, and it has a very simple and robust architecture. So first you have the laser, and then you amplify the laser light in an EDFA, so you get like 1 watt of the laser power going to an optical circulator, so where you can go in and you are forced to go out at the next exit, and it's like a British roundabout in this case. So you get all the power out here, and then by tuning the end of the fiber before the lens and the telescope, you can get some return from the fiber end, and then you also get return from the aerosols in the atmosphere, and the beating of the return from the fiber end and the return from the atmosphere, that will amplify the signal, so you get rid of all kind of noise sources except the photon noise. So the local oscillator plus the return for the atmosphere goes to a detector, and then you low pass filter, and there's also a high pass filter, and you digitize it and you make the Doppler spectra. So this is a all fiber thing, and it's pretty much like the one you have in lamps, of course. Yeah. Then the wind scanners we have now, and which are used for Eric Simley's experiment for inflow in front of a turbine, they look like this: a laser, an amplifier, then you have a beam splitter where you take a small part out, and the main part of the power go out in the atmosphere with you minimize the reflection from the fiber end. Then you get some return, and you beat that on a balance mixer with the local oscillator, which has been through an acousto-optical modulator, which changes the frequency. So now zero velocity has a non-zero Doppler frequency, and then you analyze this signal. The method that we are using in the experiments I'm going to talk about is this. So it is another way to get the sign of the velocity. Again, you have a laser, an amplifier, and then you have a beam splitter where the main power goes to the telescope and a smaller part goes on as a local oscillator, so the one you want to beat the return from the atmosphere with. You get the return from the atmosphere, and then you split both the return from the atmosphere and the return from the local oscillator into 50-50 split. And then you beat the 2 on 1 balanced mixer, a special, very good kind of detector. But the other half you put into an optical component that can change the phase by 90 degrees. And then you beat it on another detector. So these two detector currents, called in-phase and quadrature phase, they are actually also 90 degrees out of phase. And whether one is leading the other or the other way around determines the sign of the wind speed. And then you can go on and analyze the result. You can analyze the result in several ways. If you take you can take the cross spectrum between the two. If you take the cross spectrum between these two and one is 90 degrees out of phase, then you'll get a almost purely complex number, and the sign of this complex number will tell you the direction of the wind. You can also form a complex time series by taking the in-phase signal and multiply it by I times the quadrature signal, and then you get a spectrum which is not symmetric around zero, and the frequency will simply determine the velocity. But we'll see some examples of that. So this was kind of designed by Cyrus, my PhD student, and he also figured out which component to buy and build. So this is the wind scanner system. So that's the one with the acoustic optical modulator, and we have from Ebba's experiments that we saw before. We have two PDFs of the line of sight velocity one from the lidar and one from the sonic. There's a little shift that could have to do with the flow distortion, but in general they match very well. That's because they are not around zero. Then you take another path and take the same hour of data and look at what happens there. So now the sonic has a nice PDF here, but the lidar cannot measure close to zero with AOM. There's too much noise around zeros that we can extract the velocity always, at least. It depends, of course, on the measurement volume. The larger the volume, the wider the Doppler peaks and the easier everything is. But these data are from a small measurement volume because we have focused quite close to the instrument. All right, so that's a problem. So then we tried this new IQ system. This is Eximli, this is Anders Tegmeyer. This is a telescope, and these are the cables. They're going into the trunk of my car. And then we have the instrument here. You would just put it on a piece of cardboard, actually, and it's extremely stable because it's all fiber-coupled components. Then the laser is shooting more or less vertical, and the sonic is like 10 feet above the telescope, the CSAT sonic. If we look from below, this copper anemometer is way further up, so it's not of any concern. But then we can locate the beam with a kind of infrared sensitive device here and see that it's like 19 centimeters away from the center of the CSAT sonic. Well, before we were talking about ways to analyze the data. One was to form the complex time series and Fourier transform that and produce a spectrum. Another one was taking the imaginary part of the cross spectrum between the I and Q part. And we have done some theoretical calculation of the signal to noise ratios, and this is usually the signal to noise ratio is defined as the signal strength divided by the average noise. But we're not doing that here, because then the signal to noise ratio of this would be infinity, because if you have noise, the noise in the two channels, the photon noise in the two channels are completely independent, so the cross spectrum will on average be zero. There'll be no noise in the spectrum except fluctuations around zero. In this, where we take some absolute square, the noise goes up and you can see a noise floor. So this is quite advantageous. And if we define the signal to noise ratio as the signal strength above the noise level divided by the fluctuations in the noise level, then the two methods come out pretty identical. I mean, this is slightly better signal to noise ratio than that, but they are pretty identical. But this has this huge advantage of getting rid of the noise on average. Okay, so let's look at some spectra. These are spectra recorded at 60 Hertz, and this is a orthospectrum of the complex time series. You can see it's not symmetric. When the peak is over here, the velocity is positive, and when it's over here, the velocity is negative. But you also see a lot of energy right around zero, and sometimes there's leaking some of this power out from zero. This is the imaginary part of the cross spectrum. It's anti-symmetric. Actually, it's the anti-symmetric part of the orthospectrum of the complex time series. And when you have positive peak here, then it's a positive velocity. But if you have a negative peak over here, then it's a negative velocity. But the problem is that, I mean, if we had winds away from zero, this is frequency bin number, then we'd certainly use this method. But quite close to zero, if you have more or less symmetric distribution here, then, if you have a symmetric distribution here, then the anti-symmetric part would be zero, and it would be hard to measure the winds anyway. So we kind of stuck with this method where we have to do the cumbersome work of getting rid of this peak in the middle and subtracting the background, which we didn't have to do over here. Okay, so the noise. So this is the power spectral density over 1 minute in the first positive frequency bin and in the first negative frequency bin. And what you can see here is that it looks like that there's a background level of noise which varies in time, and then occasionally the real signal passes these frequencies and you get something above. So we use this to kind of determine the noise level at very close to zero frequency. And here you can see that the noise, the background noise, is as a function of bin number, consists of two terms. There's the background noise we saw before on the time varying background noise here in frequency bin plus or minus 1. And that leaks out, so we have a leaking factor here starting in 1. This is a leakage factor, and then it rapidly decreases. This is a logarithmic axis. So if 10 bins out, it's down at 100th of the noise close to zero. Then there's a more constant background which looks like this. This is on a linear axis, so it's pretty flat, and I think there's some kind of low pass filter out here that kind of cuts it off. So this is a model for the background noise. We had to subtract from all the spectra we saw before in order to calculate the noise-free Doppler spectrum. Then this is the average of all spectra. Looks very nice except around 0. At 0 frequency we have no signal. We cannot detect things that are not moving. And at the 2 frequencies close to 0, we also underestimate the spectral energy. So before we go on and determine the Doppler frequency, we interpolate between these points to get a more reasonable spectrum. Once we have the spectrum, then we determine the frequency by the median method. We find the frequency at which there's just as much power spectral density to the left and the right, instead of the center of gravity, which is more noisy. So, okay, so let's look at the resulting data. These are 60 Hertz data, and we compare the lidar and the sonic in the lidar. We compare the lidar and the sonic, and because the lidar is pointing vertically, we cross 0 all the time. And they are 20 centimeters apart, so you don't see exactly the same velocities. But you see that there seems to be smaller problems when you go close to 0. So this is the time series, 5 seconds at a time. So it looks pretty good, except maybe here something is happening. I don't know. Anyway, when we look at the PDF of the vertical velocities, and we have the sonic here, the smooth sonic here, and close to 0, we still see some problems. We still see that the lidar kind of avoids the 0 velocity. But how much does that actually mean, and how does it compare to the other situation where you had the acousto-optical modulator? As you can see, we have reduced the problem, but I would like to explain what it means in terms of centimeters per second. And the way to do that is to make a plot where you plot the lidar data versus the sonic data. And we do that by looking at the cumulative probability function and plot those against each other, and it should be more or less 1-to-1. And it looks pretty much 1-to-1, except very close to this is a zoom here of this curve. You can see here that when the lidar is measuring something, say 0.1 meters per second, then the sonic says it's actually a little less. So this is so if you apply this curve to correct the data, then you get a perfect PDF. But we cannot really do that because that's cheating, I think. But the difference here is 2-3 centimeters at most, in an interval of plus minus 20 centimeters per second. Then you see that the slope here is close to 1. That is, you shouldn't believe in this, because there's 2 opposing effects. One is that the sonic anemometer is measuring less than it really should in the vertical. But the weighting function of the lidar also reduces the vertical fluctuation, and these 2 things cancel, so you get around 1 by serendipity. If we compare with the AOM system, and it looks like that, there's really problems around 0, and you see that the functions you should apply to correct the PDF looks like this. So it means that you have differences of 20 centimeters per second in quite a wide range, at least half a meter per second, maybe up to 1 meter per second, where you have these problems. Okay, so then now we have these nice data. It would be nice to use it to see whether it fits in with Ebba's analysis. So what we do is that we calculate the spectra of the power spectral density of the lidar and the sonic as a function of frequency. And what you can see here is that at low frequencies, the lidar has higher power spectral density than the sonic, and it's vice versa at high frequency. And the crossover point is like 1 hertz. So, I mean, it looks like if we just shifted one of the curves a bit, then we'll get a perfect match at low frequencies, but less perfect match at high frequencies. So in the next plot, I'll show the ratio between these two curves, and that is a gray curve. So this is, again, frequency, but this is a ratio of the power spectral densities of the lidar and the sonic. At low frequencies, the lidar have more fluctuations, but around 1 Hertz, it has less fluctuations than the sonic anemometer. So if I, then I've calculated what should theoretically be the difference between the lidar and the sonic spectra. And there I've used, for that you need a spectral tensor model. You need to know the three-dimensional structure of turbulence, and then combine it with the work of Steve and Tom about how sonic anemometer average in space, and also how a lidar is averaging in space. And it turns out that the lidar is averaging much more than the sonic. So actually the ratio should be like this. And if you go to high frequencies, then the lidar will measure less than the sonic. So if I shift this curve, which is a ratio of the spectra if I shift it down by 4%, then I get this red curve, which fits very well with the theoretical prediction of the attenuation. So I feel pretty confident that, okay, the lidar is measuring 4% less than the lidar, which I believe is from first principle and no flow distortion. So how does that fit in with the Ebba's analysis? Well, before I go to that, we can also calculate the coherence between the lidar vertical velocity and the sonic vertical velocity. That's all the dots here, the coherence as a function of frequency. This is the theoretical coherence if we consider the lidar to measure in 1 point and the sonic in 1 point displaced by these 19 centimeters. Then you can do different things. We can calculate the averaging in the sonic and the lidar, and then that will increase the coherence up to here. But then there's also noise in both systems. And noise, if you look at the coherence, how it is defined, is the cross spectrum squared divided by the product of the orthospectra. And if you add noise to the orthospectra, then you increase the denominator, while you would not increase the numerator because noise in the lidar and the sonic are uncorrelated, so we wouldn't increase that. Anyway, by increasing the denominator, you will decrease the coherence, and that will go down to here. Not quite what is measured, but it's getting close. But it also shows that even at these 20 centimeters, you lose a lot of coherence at pretty low frequencies, 5-6 Hertz. You start to lose the coherence. Anyway, so my 4% are right here. The data were obtained from a wind direction of 102 degrees, and it fits okay with the Ebba's analysis, even though it's a completely different experiment. And that was a good surprise yesterday. No, it's not. So that was the plot from before about how the lidar measures more, and it amplifies the vertical fluctuation as measured by the sonic, and how it depends on wind direction. All right, so in conclusion, I could say that this in-phase quadrature lidar works well, except some small fluctuations in the interval plus minus 2 meters per second around 0. You get this 4%, which fits very nicely with the Ebba's results of the reduction of vertical wind speed as measured by the sonic. I would also say the deviations around 0 velocity, they depend on two things. They depend, in fact, on the length of the FFT. We haven't really tested that, but I'd like to do. And it also depends on the measurement volume. If we have a larger measurement volume, then all the Doppler peaks would be wider, and it's easier to kind of interpolate through zero. Yeah. Okay, so that's it. Thank you very much. And
Scott? What was your bin size? What FFT size were you using?
512 points, and it's a 100 megahertz sampling rate, so that corresponds to 15 centimeter per second steps in velocity, in Doppler velocity. And usually we can get a much higher precision because we have power spectra covering many bins. But sometimes, and I think we can see it here, yeah, sometimes if we don't have a lot of power or the turbulence is low, then we can only get the multiples of 15 centimeters per second. That's actually something you see here in the lidar histogram, that sometimes you get these lines here, that is multiples of 15 centimeters per second.
So in your conclusion, you only mentioned about vertical velocity. Is that because you only have a one modified lidar to compare with CSAT? No?
Yeah, in this experiment, the second experiment here, we only used one, and we used this new architecture for the lidar, and then we proved that it was better. But Ebba's conclusion is about all components. Yeah.
This is a question a little bit off, but the Zephyr lidars, they're the conical scanning things, and I'm guessing they do some kind of VAD technique to measure winds, and so perhaps it's not so much a problem for measuring wind measurements if they have trouble near zero, because they're primarily using winds that are away from zero. Or am I thinking about?
Yeah, I mean, you will see that the problem is largest when you have low winds. Then it's more difficult to fit a rectified cosine. And also they have to have a little vane or something on us. They have to measure the wind direction crudely on the instrument, so they can see whether the wind direction is this or it's this. So if they used the IQ architecture, then they wouldn't need the crude wind direction measurement, and they could also measure down to lower velocity.
So is your IQ method automated, or is it taking a lot of number of
All the stuff with getting rid of the background and problems around zero. Well, it's not implemented in a system now, but we are remodeling our three wind scanners. It's short-range wind scanners, as we call them, to have the new architecture, and then it will be implemented in those. Actually, we have one system that we sold to University of Western Ontario, where this procedure is implemented. Yeah, but that is the first system where it's implemented, but we'll implement it again in our own system, maybe improve it.
Well, there are some more questions. Jakob will still be here